This tutorial is going to talk about section 4.3, Riemann sums and definite integrals. So the first thing that we want to talk about is what a Riemann sum is. And in its most simplest terms, it's sums of areas of geometric shapes with equal width. And the most commonly used geometric shape that we're going to start about learning is with rectangles. And more importantly, what we're going to use Riemann sums for is to find the area under curves. And integrals are what's going to help us because integrals help determine area under curves. So let's take a look at a very simple example. So let's take this picture for example. This is just some random function. And I want to determine the area bounded by the y-axis and the x-axis and all the way up to, let's just say some value will go all the way up to 4. Okay, and I want to know the area of this part right here. I'm going to shade it in for you. I want to know the area here. And as you can tell, that would be really hard to do if you don't have a perfect circle. Alright, so let's go ahead and get this started. Now, we want all of our rectangles to have an equal width. So they're all going to have, in this example, a width of 1. Think about it in this way. The more rectangles I have under this figure, the more accurate my area is going to be. So we're going to start by making some rectangles. So here is one of them. Now I have to start with an endpoint on my circle. That's really important. Okay. Now I'm going to make the next rectangle here by continuing this line upwards until I hit my function, so I have my next endpoint. Carry that across and down, that makes my next rectangle. So do the same thing again. Carry that line back up until it hits the function. Carry it over. It's okay if it goes above the line, and then bring it down. And then this would be the top of my function now. Bring it over and then down. So if I were to find the area of each of these individual rectangles and add them up, that would give me a Riemann sum. And Riemann sums get the beautiful sigma notation, which is this. Okay, that means sum. So I would add up, and I'm going to call this figure A, B, C, and D. I would add up the areas of A and B and C and D, and whatever that sum is the area under that curve. Now notice that this is not going to be very accurate because we're missing a lot of pieces. This here is an underestimate because I'm missing this huge space of area here, and then of course over here I go over a little bit and all that good stuff. So the more rectangles that you can use, the better your approximation is going to be. Now if you're trying to find the area between two specific values, in this case it was between 0 and 4, that should tell you that that is something definite. I'm looking for a definite area. And since area and integral coincide with each other, that means a definite integral. So how could I set it up like this? First of all, I'm going to go ahead and give this function name. Let's call it g of x. So the way I would write a definite integral for this is I'm going to write my integral sign like this. Okay. Now, the value farthest to the left goes at the bottom of this integral. So I went all the way to 0. So 0 is going to go down here. The farthest to the right I went was 4. So 4 is going to go up here. Now, what goes over here is just whatever our function is. So in this case, it's g of x. And of course, we have to write whatever we're taking the integral with respect to, which is dx. So that's how you can write a definite integral. And as you can hopefully notice, this right here is the same exact idea as this right here. They are two of the same exact ideas. Now, how do you actually go about doing a definite integral? Well, let's take a look at an example. So let's take a look at this problem. This is the definite integral from -2 to +1 of the function 2x and with respect to x. So before we can actually evaluate anything, we have to actually determine what the integral is. Now this looks like it's just a basic step here. Then since this 2 is a coefficient, I don't have to worry about it. I'm going to pull them outside of the integral itself. So negative 2 to 1. Leave the x inside. And this x right now has an exponent of 1. Alright, now if you remember your integral rules properly, that means I add 1 to that exponent and then divide by that same exact sum. Now, if this was an indefinite integral, I could leave this just like that, but I still have to make sure that I know that I'm going between two different values. And you can use one of two things. You can either use a straight bar from negative 2 to positive 1, like that, or you can use a bracket, like this, negative 2 to positive 1. It works the same exact way. It's not going to alter your problem, so you choose which one you like the most. So let's go ahead and simplify this. So this is going to give me 2 times, it looks like x squared over 2 between negative 2 and 1. Now these 2's are going to cancel here, so they're gone. So now I have x squared alone from negative 2 to positive 1. So the way to evaluate this is we're going to take the larger, or the value farthest to the right, and we're going to plug that in first, which is always our top number. So I'm going to plug 1 into this function. So 1 squared is 1. All right. Now, I'm going to subtract the value that I get from my smaller value here. So negative 2 squared is positive 4. And I go ahead and evaluate that, and that gives me negative 3. So the area under that curve between negative 2 and positive 1 is negative 3. And that's the very basics of this, and that's what I need you to know the most. That concludes this tutorial.